Alright, let's talk about chapter 3. We're going to do kinematics in 2 dimensions. And how we do that is with something called vectors. So we're going to talk about vectors, splitting up a velocity vector into an x and y component, doing kinematics in one or the other direction, and then recombining them at the end. And then projectile motion is like a punter in a football game or during kickoff. Whenever you kick the ball and it makes a big arch like that, that is called projectile motion. Shooting a bow and arrow into the air, throwing a baseball, throwing anything, shooting a basketball, that's all projectile motion. Launching a rocket, whatever it is. Okay, so kinematics in 2 dimensions. We talked about our vectors here. If you're trying to get to this point in the city, you have to walk over and up. You probably can't walk straight because you'll walk through a bunch of buildings. But you can walk, maybe a zigzag like that. Okay, whatever. So you walk 9 blocks east and 5 blocks north. Okay, that's a vector actually. That is the x component and the y component of a vector, and that is the vector that has those components. So this hypotenuse has a x side and a y side. So we represent that with an object called a vector. And we could say that this vector we draw with an arrow on the top of it is equal to, in this case, 9 blocks in the east direction plus 5 blocks in the north direction. I could write that vector this way, and that simply means go 9 blocks east and then go 5 blocks north. And that corresponds to that triangle. If I want to know how long that triangle is, it's just 9 squared plus 5 squared and square root. So this is 9 squared plus 5 squared. Because Pythagorean theorem holds even for this thing, okay? And there we go. So there's your Pythagorean theorem to get the length of the side of a triangle that has sides A and B. If you want to get side C, it's just A squared plus B squared, and then square root that. And so there you go. There's your total distance. If a helicopter made that same flight, they would only have to travel 10 blocks instead of 9 plus 5 is 14 blocks. So you can see you can save some time there. Now, the important thing for why we do this is because gravity, we talked about an object in free fall. Gravity only affects the y direction. If you have something moving in the x direction, when you throw it, the y component of it will behave like normal. The x component will just go like rate times time equals distance. And so the distance over time changes at a constant rate because there's no acceleration, so you have constant velocity. So that's what that's trying to show here. 2 identical balls, one ball you dropped, and the other one you tossed horizontally. And what you see is that the y at every instance of time, tick, 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 same instance of time, the balls have the same y value, the same y coordinate, because they're falling at the same rate. The difference between the orange and the blue ball is that this guy over here is going to hit the ground over here. This guy is going to hit the ground here. How far over is this ball? Rate times time equals distance. It's this far away, however long it took to fall, times the distance it was initially in the x direction. So we can split the x and y components up, and that's this kinematics in 2 dimensions that we're talking about. So how you add and subtract vectors is simple. You just add up the head-to-tail method. So if you want to go, let's say if someone told you 9 blocks east and then 5 blocks north, to add those 2 vectors up, you have your first vector and your second vector. This is the head of any vector, that's the tail of any vector. So if you have a vector, head and tail, okay, you've got another vector, head and tail, you're going to do head to tail method, so you're going to take the head of this vector and touch it against the tail of that vector. When you do that, you get dink dink, okay, the head of this vector and the tail of this vector are now at the same point, and the result of this plus that gives us that vector. Okay, so that's called the head to tail method of adding 2 vectors. And it's literally you take the vectors, the 2 vectors, you don't change their anything about them. You can move this vector, you can move it over, you can move it up here, you can do anything. You cannot rotate it because that would change the direction. You can't change the magnitude, so you can't make it longer or shorter in order to keep it the same vector. So if you want to figure out what happens if you go this far over and that far over, it might seem obvious, you just go over and up like that, but that process is actually called the head-to-tail method, and that's how that works. Alright, so that's what they're just going through there, different examples. So adding vectors graphically, A, B, C added up. If you add A plus B plus C, the result of A plus B plus C is that vector called the resultant. You didn't have to do anything, you just put them head to tail to figure out the resultant. So if you walk this far, then that far, then this far, your resultant is there. That's how far away from home you are. Okay, so it's not very difficult. It's simply don't change the vectors, don't make them longer or rotate them, but you can translate them around until the head of one is touching the tail of the other. So the head and tail, head to tail, and then that's the ending part, and so then the resultant, boom, is there. Okay, so this vector is the exact same as that vector, but a minus sign means you just put the arrow on the other side. So a minus sign just swaps the head and the tail together, otherwise the vector is the same. Those are just some general rules. There's some other examples here. Okay, so that's the pictorial method of adding vectors together. There's the analytical method where you break a vector up into its x and y components. So here's what I did earlier. I said you had a vector, and I said 9 blocks east and 5 blocks north. So every vector can be written as a sum of components. So this vector A has x and y components. Okay, so if I have any vector, let me draw a new vector. There's my vector. Okay, that vector has that component in the x direction is how far over do you have to go, and this component in the y direction, how far up do you have to go. Okay, and those things give you the vectors. Okay, so how do you figure out the components of a vector? You use Pythagorean theorem. You use SOHCAHTOA. SOHCAHTOA. Okay, this side is the adjacent side over the hypotenuse. So cosine of theta is going to give you the ratio of ax over a. So then cosine theta times a will give you ax. So this equation here, ax equals a cosine theta, is the same as cosine theta equals adjacent ax over hypotenuse a. So then you bring the a up here and you get a cosine theta equals ax. Okay, and that's where that comes from. And then you do the same thing for the sine here to get the y component. So you can take the length of any vector, let's say this is 5, and let's say this is 20 degrees. Okay, if I want to know how long this side is, I'm going to take 5 times the cosine of 20 degrees, and that number, might be 0.1 or something like that. So then, yeah, there's no calculator built into an iPad, if you can believe that, and I don't think I have a calculator installed. So whatever, I'll use my phone. Okay, so let's do that. So the cosine of 20, oops, I'm in radians, go to degrees. The cosine of 20 times 5 is 4.69. Okay, so cosine of 20 degrees is 0.9 or something. So I got 4.7. So that means the side of this triangle is 4.7. Obviously this is not 20 degrees, this is more like 50 degrees. So if we do 50 degrees, cosine of 50 times 5, then I get 3. Okay, so this is 3.2, this side of the triangle. And so then you could solve for the other side. You could either use sine to do that, or you could do 5 squared minus 3 squared would equal the other side squared. Okay, so hopefully you see that you can break a vector up into x and y components. The vector never changes. You can have a new coordinate system. You just have different components in that coordinate system. The components will change. For example, if that was my x and y coordinate system, then in this coordinate system, that distance is going to be my new x distance. You can see that's way longer than this distance, but my y component is going to be really short. There's my y component. So your components always have to add up to the actual vector. So if you change your coordinate system, your components just can change proportionally. So ax might go up, but ay would have to go down, or ay will go up, but ax would have to go down. Okay, so here's your relationship. Another example. The length of a, the magnitude of your vector a, is just the x component squared plus the y component squared. Again, there's your right triangle. Almost all of college physics is, where's the right triangle? Okay, so these are examples of going through that. Now, you have two vectors. A vector, B vector, head to tail methods. We're adding the two vectors together. We're going to take the x component of A, the x component of B. When you add those two together, I get a new line, which is this long. It's the two added together. And then when I add the y component of A and the y component of B, you see that I get a vector that's long. So there's my new resultant with the component here and the component here, which is the result of adding the individual components of A and B. So if I want to get my vector r, it's going to be the component of ax plus the component of bx, and that's going to be my new direction in the, let me see if I've got that. Yeah, okay. So ax plus bx in the x direction plus ay plus by in the y direction. So all that means is if I want to get the resultant vector, a new vector, by adding a and b, I add the x component of a and the x component of b together, and that's my new x component of my new final vector. And if I want to get the y component of this, I add the y components together, and there they are. So it's as simple as adding up all the individual components, okay? So that's easier than, well, not easier than drawing a picture and connecting dots, but easier than trying to do a bunch of algebra and a bunch of different things. Okay, so there's your x components added up and your y components added up to give the full new vector, okay? And there you go. Wow, excuse me. How rude. Okay, so that's an example of adding vectors. Okay, so for projectile motion then, the reason we need all of that before we get into projectile motion is because when you first kick a soccer ball, it's going to have an initial direction. Okay, so let's look. When you first kick a soccer ball, boom, there is your initial velocity. You kicked it at 10 meters per second, and which is fast. Okay, 5 meters per second. You kicked it with 5 meters per second there. All right, what does that mean? It means part of your kick is going, the energy is helping put it up in the air, and another part of your energy is moving it to the right, making it go further downfield. Okay, so if you think about it, okay, if you kicked it straight up, it would not go over at all, and if you kicked it straight over, it would not go up at all, right? So by kicking it at an angle, theta, some of it is going to be, some of its initial velocity will be used to put it in the air, and some of its velocity will be used to put it downfield. What proportion it is depends on the angle. If it's 90 degrees, your velocity is straight up in the y direction. If it's 0 degrees, it's straight over in the x direction. If it's some combination, then your velocity vector equals some combination in the x direction plus some combination in the y direction. Okay? And now we have a vector. We've got an x component and a y component. Okay? So that's what we need to do when we solve these projectile motion problems, because this ball, as it goes up, look at this. That is the this is the x component of your velocity. Look at that arrow. That blue arrow is the same length every time. That means you have no acceleration because that velocity vector for v0x doesn't change. What does change? Look at this orange vector. As it goes up into the air, it gets shorter and shorter and shorter until we get here, you have no more y velocity in the air. Why? Because that's when it turns around and starts falling back down. Okay? And now your velocity vector starts growing again. What causes a velocity vector to change? In order to lengthen or shorten a vector, you need to apply an acceleration. What's applying the acceleration? Gravity. Okay? So, you've kicked this ball up in the air, but now gravity starts decelerating it. It's only going to decelerate it in the y direction. So you can use v squared equals v0 squared plus 2ay here final, at the top of this thing, the final velocity is going to be 0. So you're going to have 0 equals v0 squared plus 2ay. You can figure out how high the ball is going to go. Now, just like you would do if you toss the ball straight up and down. But if I tell you I kicked it with 5 meters per second, 30 degrees above the horizontal, you cannot use 5 meters per second for your v0 squared. You have to use v0 sine of theta, because you want the y component of the velocity vector. So the y component is what you want here, and the y component is v0 sine theta. So if I kicked it at 5 meters per second times the sine of the angle, 30 degrees, then that's going to be my v0y. Now I can use my kinematics equation for tossing a ball straight up in the air, because this velocity is the only velocity that is affected by gravity. Okay, so then if I want to figure out how far the ball is going to go, what I can do is say that, well, I know my initial velocity in the x direction is equal to my initial velocity times the cosine of theta, and I know I have no acceleration, so if I know how long it's in the air, then velocity times time is equal to the distance I'm going to travel. Okay, and that'll be my full distance. So what you need to do then is go back to the other equation and then solve for t, and then once you get your time that the ball is in the air for, double it, to get the full time that the ball is in the air. Use that time in this equation to get your range, or how far downfield it goes. Okay, so if we look at this, the x velocities are the same at every point in time. In this case, the y velocities start out big, go to 0, and then end up flipping around and going negative. So you have an acceleration there. And then right at the end, you see that your net velocity vector is the purple. It's the combination of, so at every moment in time, that's the direction that the ball is moving. Over at the top, it's only moving in the right direction, and that vector is the same length as the blue line because everything's moving in the x direction. Okay? All right, so that's all you do. That's literally what you do over and over again. You get an initial velocity, you calculate the x and y components. For the y component, you do your regular toss problem, straight up and down, and for the x component, you just do rate times time is distance, and you can solve your time, the time with this equation as well. Once you get the height, y equals 1/2 gt squared, you can figure out how long you were in the air for if you rose that high from that initial velocity. Okay, you know what, v0t plus 1/2 gt squared. Okay, and yeah, so here's a couple examples of using that to figure out how tall something goes. You're going to see this equation all the time, and all these problems are the same. They might just change the, what they're talking about. But, okay, projectile motion. You've got your regular equations, you do your same things, you find your x and y things. This trajectory here, you can solve for the time when it crosses here. You can solve for when it hits the ground at some later time t, because your position versus time graph will be a quadratic equation, and then you can solve for the time that, for the location where it's at, using this formula. Won't do that too often, but you should do that a couple times in your life. Use the quadratic formula. Okay, quadratic formula, remember, if you have a parabola, there's two solutions when the value equals 0. That's what you use the quadratic formula for. It's opposite of b. Why is it plus or minus? Because it gives you this value or it gives you that value. You have two options. Opposite of b, plus or minus the square root of b squared, minus 4ac all over 2a. Okay, that is the formula for solving a quadratic equation like y equals 1/2 at squared plus v0t. We've got t in two spots. This is a, that's b, c is your initial position, etc. And you can solve for what t is. You're going to have one t is going to be the time when you kicked it off, so it might be 0. The other t will be boop, when it crosses at that point, okay, at that position. Okay, so to get something to go the farthest, if you want the range to be the furthest when you kick it, you have to launch it at 45 degrees. 45 degrees will give you the furthest distance, will give you the longest time in the air, and the furthest, highest amount of velocity over to the right. Okay, The range on level ground of a projectile is given by this equation. We use that occasionally, but not super often. This is an example of what you have to do to put something in orbit. You have to make it go fast enough so that it's outrunning the curvature of the Earth, basically. Okay, addition of velocities. If the boat's moving with that vector and the river's moving with that vector, the boat is going to travel along this line, the sum of the two velocities. So it's just adding vectors together. You just got your x and your y components, just add them up. So if your river's flowing this way and your boat's going that way, that's the velocity, the net velocity you're going to have. Okay, and you just add them up just like normal. Okay, so go through those examples just to understand how to add those velocities together and get your net velocities. All right. Yeah, there's some other examples here, and that's the end. Okay, see you guys tomorrow.